There's this ghost in the machine. It's a silent, hidden bug that, I swear, haunts just about every single beginner's Unity project. It's this phantom problem that makes your game feel absolutely perfect on your computer, but then turns it into a completely unplayable mess for everybody else. Well, today, we're going ghost hunting. We are going to find this bug, we're going to expose it, and we are going to banish it from your projects for good.
Man, I will never forget the first time this happened to me. I had spent like a month just perfecting the controls for this little racing game. The car handled like a dream, the drifts were just chef's kiss, perfect. I was so proud of it. I sent the build to my friend who has a way faster gaming PC than my little development laptop, and he sends me back this video. The car was just a blur. It was rocketing off the track if he even breathed on the keyboard. It was a complete disaster. And that right there was my very hard lesson in how game engines like Unity actually think about time.
So here's our game plan for this explainer. First, we're going to uncover that hidden inconsistency, and I'll explain why thinking in terms of per frame is a total trap. Then we'll dig into the simple math that shows why fast and slow computers create absolute chaos. After that, we'll introduce the hero of our story, the beautiful, elegant solution called Time.delta Time. Then, I'm going to walk you through, line by line, a precise coding guide to get this fix into your own game. And finally, we'll get into the fun part, tuning our game to get that perfect professional feel.
All right, let's pull back the curtain on this thing. The real culprit here is a function you've probably used a million times in Unity. It's called update. Now, I want you to think of your game like a flipbook. You draw a little stick figure on each page, and each page is one frame. The update function is the action that you draw on each one of those pages. So when you flip the pages, the action happens. The faster you flip those pages, the faster the action happens. And that right there is where our whole problem starts.
Oh man, this is the classic scenario, isn't it? I think every new developer has lived this. On your machine, your trusty development PC where you've done all your testing, the game is flawless. The character's jump is perfect, the car turns exactly how you want it to, but then your friend with the high-end gaming rig tries it, and the car just zips around like it's on a sheet of ice. And another friend with an older laptop says it feels like they're driving through thick mud. The experience is totally different for everyone. And let me tell you, for a player, inconsistency is the fastest way to get them to just quit your game and never come back.
To really get to the bottom of this, we need to talk about frame rate, or what you'll always hear called FPS. Imagine your computer's a painter, and your screen is the canvas. FPS is just how many new paintings it can crank out and show you in 1 second. So a really powerful gaming computer, it's like a master painter, right? It's churning out 150 paintings a second, no problem. A less powerful computer, maybe an older laptop, is more like a student painter. It's trying its best, but maybe it only manages 30. But here's the kicker. Even that master painter gets tired. When there's a huge explosion on screen or 100 enemies, the number of paintings it can create per second drops. And that variability, is the ghost in our machine.
Okay, so let's see how this all spirals into pure chaos. We're going to look at some really simple math that shows exactly why these different frame rates just completely break our game. Trust me, this is where it's all going to click. Let's set up a really simple rule for our game. Inside our update function, that's our instruction for each page of the flipbook, we're going to write one line of code. Move our car forward by 1 unit. That's it. This command is going to run every single time the computer draws a new frame. Seems logical, right? Well, let's see what happens when two totally different people play our game. So first up, we have the slow computer. It's just chugging along at a measly 10 frames per second. That means in 1 single second, it's only able to draw 10 pictures. Now for each of those 10 frames, our code tells the car to move forward 1 unit. So you do the math. After 1 second has passed, the car has moved a grand total of 10 units. It's just kind of inching along the track.
But now, look at the fast computer. This thing is a beast. It's running at a blazing 100 frames per second. It is running the exact same code, move 1 unit per frame. But because its update loop runs 100 times every single second, the car moves a staggering 100 units in that same 1 second period. That's 10 times further. Suddenly our game's speed, the entire feel of the game is completely tied to how much money the player spent on their graphics card. And that is a disaster. And this brings us to what is basically the golden rule of professional game development. Your game must feel the same for everyone, everywhere. It shouldn't matter if they're playing on a supercomputer that costs thousands of dollars or a 5-year-old laptop they dug out of a closet. The experience has to be consistent. We call this frame rate independence, and honestly, it's one of the biggest things that separates the pros from the amateurs.
So how do we do it? How do we enforce this golden rule and get that consistency? Well, thankfully, Unity gives us a beautifully simple, incredibly powerful tool built specifically for this. It's called Time.delta Time. This is our magic wand. This is how we are going to take back control over time itself in our game.
Okay, so what exactly is this magic variable? Time.delta time is just a tiny little decimal number that Unity calculates for us automatically every single frame. It literally represents the exact amount of time, in seconds, that it took to draw the last frame. So on a fast computer where frames are finished in a flash, this number will be really small, something like 0.01. But on a slow computer where each frame takes longer to draw, the number will be bigger, like 0.1. It's a perfect, real-time measurement of how fast our game is running.
Okay, let's put our math hats back on. But this time, we've got our secret weapon, Time.delta Time. Let's look at the slow computer again at 10 FPS. Each frame takes about 0.1 seconds. So for each of its 10 frames, we multiply our 1 unit of movement by 0.1. At the end of 1 second, the total movement is 10 units. Now look at the fast computer at 100 FPS. Each frame only takes about 0.01 seconds. So for each of its 100 frames, we multiply our 1 unit of movement by 0.01. And what's the result? It's still 10 units per second. It's like magic. The result is now identical. It doesn't matter how fast the computer is.
And this right here is the core concept. If you take away just one thing from this entire explainer, let it be this. By multiplying our movement value by Time.delta time, we have fundamentally changed what we're asking the computer to do. We are no longer telling the game to move a certain distance per frame, which is an unreliable, shaky unit of measurement. We are now telling it to move at a certain speed in units per second, a constant, reliable measure of time that we can all agree on.
All right, enough theory. Let's get our hands dirty and actually put this into practice. In this section, we're going to jump right into a C# script and apply this fix to our car controller, and you're going to see just how shockingly simple it really is.
Okay, here's our plan of attack. It's super simple. First, we're going to open our player controller script. You can just find it in your project window. Then, inside that script, we're going to find the update method, where all our movement logic lives. After that, we just need to change 2 little lines of code, one for steering left and right, and one for moving forward and back. That's it. It's a quick 2-step fix that solves the entire problem.
First up, let's tackle the steering. Right now, our car's steering speed is completely chained to the frame rate. That means on a fast PC, the steering is going to feel super sensitive and twitchy, and on a slow PC, it'll feel heavy and unresponsive. We need to make it feel the same for everyone.
Okay, take a look at the screen. This code should look pretty familiar to a lot of you. We're calling input.getAxis horizontal, which just gives us a value between -1 and 1 if the player is hitting A and D or using a joystick. Then we multiply it by a variable we made called steer speed. And this whole thing happens every single frame, which, as we now know, is the source of all our problems.
And here's the fix. It is literally this simple. All we do is go to the end of that line and we add Time.delta time. That's it. That's the whole thing. Just by adding that one little piece of code, we've transformed our calculation from a steering amount per frame to a consistent, reliable steering rate per second.
Perfect. Now let's do the exact same thing for moving forward and backward. The principle is 100% identical. We've got to unchain the car's acceleration from the player's hardware so it moves at the same speed no matter who is playing.
So here's our original code for movement. Looks just like the steering code, doesn't it? It gets the input for the W and S keys, and it multiplies it by our move speed variable. And just like before, this is frame rate dependent, and it's going to cause crazy inconsistent speeds on different computers. And once again, the solution is just beautifully simple. We just pop Time.delta time right on the end of the line. And just like that, we have now made both our steering and our movement completely frame rate independent. Go ahead and save your script, and let's jump back into the Unity editor.
Okay, we've put the code in, we've saved the script, our game is now technically correct. It's going to run consistently on any computer out there. But when you jump back into Unity and you smash that play button, you're going to notice something a little unexpected. So let's talk about how we turn this bug fix into a feature by tuning our game to get that perfect feel.
So you hit play, you're all excited, you hold down the W key and what? The car barely moves. It feels like it's crawling at a snail's pace. And your first thought is probably going to be, oh no, what did I do? Did I break it? No, you didn't break it. In fact, this is exactly what's supposed to happen, and it's proof that our fix is working perfectly.
Here's why it's so slow.
Just remember, time.delta time is a really small decimal number, right? Like 0.016 if you're running at 60 FPS. So by multiplying our speed by this tiny little fraction, we've massively reduced the final movement value each frame. Our original move speed and steer speed variables, they were balanced for a per frame world. Now that we're living in a per second world, those old values are just way too small. We just need to pump them up to compensate.
And here's where the real fun begins, because we can do this live. This is one of the most powerful features in Unity. First, just press the play button at the top of the editor. Now, while the game is running, go find your car object in the hierarchy window on the left and just click on it. Then, look over to the inspector window on the right. You'll see your script component there with our public move speed and steer speed variables. And here's the cool part. You can actually type new numbers into these fields while the game is playing to feel the results in real time.
So since our old values, which were probably something like 5 or 10, are totally useless now, let's just start with a big jump to see what happens. I'm going to change both steer speed and move speed to 100. Just go in there, type 100 into both fields, and hit Enter. Now click back into the game window so you can drive the car, and let's give it a test.
Okay, so what did we learn? For me, with the movement at 100, whoa, that is way too fast. The car just rockets off the screen instantly. It's completely uncontrollable. But the steering at 100 doesn't actually feel too bad. It's responsive, maybe a little loose, but it's in the right ballpark. So this tells me our final movement speed needs to be a lot lower than 100, and our steering speed is probably going to end up being higher than 100. See, this is all just an iterative process of dialing in the feel. It's more of an art than a science. So based on that first test, I'm going to bring the move speed way down. Let's try 20. And since the steering felt pretty good, but I want it to be a bit snappier for more of an arcade feel, let's double that steer speed to 200. I'll type those in, and now let's test drive it again. Okay, testing this out. A movement speed of 20? Yeah, that feels great. It's fast enough to be fun, but I still feel like I'm in control. It has a nice sense of acceleration without just being overwhelming. I think 20 is the magic number for my forward and backward movement. I'm happy with that.
Now for the steering. 200 was good, but I want it to feel really nice and snappy, so you can make these quick responsive turns. So I'm going to bump that value up one more time. Let's try 300. I'll test it out. Yes, that's it. It feels agile, it feels responsive, it's exactly how I want my car to handle. So my final values are 20 for move speed and 300 for steer speed.
Now, stop. Before you do anything else, listen to me very carefully. This is the single most common mistake that new Unity developers make, and it is absolutely heartbreaking when it happens to you. Any changes you make to values in the inspector while the game is in play mode are temporary. The second you press that play button again to stop the game, they are going to revert back to what they were before. So please write down or remember the values you liked. For me, that's move speed 20 and steer speed 300.
So this last step is absolutely crucial. Click the play button to exit play mode. You'll see your speed variables in the inspector just snap right back to their old tiny values. Now, with the game stopped, you need to manually type in those new values that you found during your tuning session, 20 for move speed and 300 for steer speed. Now, and only now, are they actually saved for good.
And remember, the values I picked, 20 and 300, that's just what felt right to me for the kind of arcadey racing game I'm picturing. You are the game designer. Your game should feel the way you want your game to feel. Maybe you want a slower, heavier truck that takes these big, wide turns. Well, in that case, your move speed might be 15 and your steer speed might be 75. Just play with these numbers. Tweak them until you get a result that makes you smile.
So there you have it. We've hunted down the ghost in the machine. We've not only fixed a critical, game-breaking bug that makes games feel inconsistent, but we've actually unlocked a whole new level of precise control over the core feel of our game. We've gone from being at the mercy of the player's hardware to being the true masters of our game's physics and timing. The only question left is, with this newfound power and this newfound precision, what are you going to create?